Hello everyone, this is Jude Leonard from Department of Physics, St. Joseph's College of Arts and Science, Kadalur. Here we are going to discuss about two types of diffractions. One is electron and one is neutron. And this starts with the definition of diffraction. Diffraction is a phenomena when a wave encounters an obstacle. Due to that obstacle, it bends and a phenomena occurs, and this phenomena is called as diffraction, and the pattern happens because of that is called as diffraction pattern. And this occurs when a beam of ray from collimator gets collimated and strikes the pair of parallel lattice, that is lattice points in a crystal or in a material. Due to that obstacle diffraction, there is a scattering, and after the scattering the secondary waves that interfere each other produces the diffracted image. Here we are going to discuss about two types of diffractions. One is electron and one is neutron. And this shows how X-rays differs from electron waves. We can also associate the fast moving electrons, highly accelerated electrons, with its wave properties. And the equation, we all know that lambda is equal to h by p. P is the momentum mass into velocity, and h is Planck's constant. M is the mass of the electron, that is 9.11 to the power of minus 31 kilogram, and V is the velocity, which depends upon the accelerating potential given to the cathode and anode. Usually the lambda varies between 3.89 to 0.12 angstrom units, and voltage is highly accelerated voltage from 10 to 10,000 volts. During such high voltage, the electrons get highly accelerated and access X-rays towards the target material, crystal, let it be a crystal, and due to this high applied voltage, the electrons get scattered in the lattice point, as we mentioned earlier, and diffraction pattern appears. This shows the diffracted image pattern of a sample. This is an example of a diffracted image. By applying a very high voltage up to 40,000 volts, the electrons get accelerated and it is scattered by the lattice points, and the image of the sample, the crystal structure and image, the diffracted image occurs on the fluorescent screen, as you see over here. It is in different forms, concentric rings, and the pattern differs from sample to sample. Here we can see the applications of electron diffraction. It is highly used to investigate the nature of the solid surfaces and surface films. The coated surface films and their samples are usually investigate by using this electron diffraction phenomena or method. The surface structures of the sample are easily studied using this, and this method is highly effective for gases and vapors. The samples in the form of gases and vapors can be easily identified by using this particular method, and for measuring bond distances and bond angles. At a particular angle, what could be the structure, that is the lattice points are located, the angle between the surface lattice planes, and measuring the distances between those bonds can be highly effective by applying this method. And it provides the information about the electron distribution in the given sample. The electron distribution, the lattice points in the given sample how it is distributed within the structure, or it may be affected by the defects. All these kinds of information can be provided by using this particular method. This is the advantage of electron diffraction over X-ray diffraction. As we know that it is highly penetrable than X-rays, and their interaction with the surface level is more intimate when comparing to X-ray diffraction. And in electron diffraction, the intensity of diffraction pattern is high, and it is somewhat good over than the X-ray diffraction, where you can get the clear intensity of diffraction patterns in the fluorescent screen. And so only very short exposure time, we require a very short exposure time to get the diffracted image pattern of the sample. All these are advantages of electron diffractometer diffraction phenomena over the X-ray diffraction phenomena. The next phenomenon is neutron diffraction. As the name means, the neutron is used as a source material, and it is the application of a neutron similarly to the electron diffraction, and it happens due to the scattering of lattice points to study the atomic structure in detail. And these source neutrons are collected from a reactor. It is their velocity is slowed down and it is in the appropriate speed, and the wavelength is adjusted so it lies between nearly 1 angstrom, that is 0.1 nanometers. As we know that is the atomic distance, the separation between the two lattice points in the solid material, typically in the solid material, so that we can use neutron instead of X-ray or electron to study the as well as the as we already insist, that is bond angle and bond length. Such a beam is used to perform a diffraction pattern, to get a diffraction pattern, and electron is replaced by neutron. This is the schematic representation, the instrumentation of the neutron diffraction. The source here, the source is neutron, and then the source of the neutron is usually from a nuclear reactor, and it is altered by using a monochromator or a kind of crystal monochromators. So their wavelengths has to be 0.1 nanometers, nearly equal to X-rays, so that it can easily measure the various factors of that particular sample, as well as filters are also used to get these kinds of desired neutron wavelength. Here in neutron diffraction, two types of scattering mainly occurs. One is nuclear, another one is magnetic scattering. And this shows the about nuclear scattering. The image shows the scattering effect, and this happens due to the interaction of the source material neutron with the atomic nuclei, and this differs to each isotopes. There is a difference in the intensity pattern due to the scattering of these neutrons in the atoms in the lattice sites get a diffracted image. It is seen often that low atomic number atoms contribute very strongly to the diffracted intensity, even in the presence of large atomic number atoms. The second type of scattering is magnetic scattering, and although neutrons, we know that it is uncharged since it carries the magnetic moment within it, and therefore interaction with the magnetic moments also occurs, and this results in the electron cloud around the atom. There is an interaction of this magnetic moment with the electronic cloud of atom, so there is also a magnetic scattering happens, and therefore it reveals the microscopic magnetic structure. Since it happens the magnetic scattering over there with the material, it also reveals about the magnetic structure, and this scattering requires an atomic form factor, and it is caused by the much larger electron cloud around a tiny nucleus. When this happens, the magnetic scattering requires the atomic form factor 2. And the applications of neutron diffraction is, it is used to locate the light atoms. Since neutron is used as a source, it is useful to detect the various types of isotopes. As you know, isotopes of same atomic number can be identified by using this neutron diffraction process or method, and it is useful for the analysis of called nuclear activation analysis in the nuclear processes for determining the concentration of the elements. When there is a vast amount of materials happens to be in a particular sample, the concentrations of a particular element can be used to identify by using this adopting this method. We know that it is highly penetrating, and it can be used to measure the bulk properties of very large samples, and we know that it has the magnetic property. So due to the magnetic scattering effect, it is also useful to study the magnetic properties of the compounds compressed of a transition metal series. These are some of the differences between electron and neutron diffraction. In electron diffraction, it is negative in charge, and this provides the information about the surface structure. It provides only the surface structure, information of the surface structure, and whereas in neutron diffraction, we know that it is highly penetrating. Due to its nil charge, it can study the internal structure of the material, not only the surface but also the internal structure of the material. The second point is electron diffraction. It has a strong interaction with the electron clouds, and it also scatters from heavier elements. In neutron diffraction, the scatters occurs due to the interaction of both the lighter and heavier atoms. Electron diffraction is used to study the magnetic property of the samples and the interaction of the magnetic properties with electromagnetic radiations. And in neutron diffraction, we know that neutrons of spin -1/2, and it also possesses the magnetic moment. It has the magnetic scattering effect due to its magnetic moment. Since it has that particular property, we can easily identify the magnetic properties of the sample, but it has the over a short range. And electron diffraction is less expensive, and it can be used under a less cost. And whereas neutron diffraction, so it should be, the source has to be collected from the nuclear reactor, and there are certain precautions to be added, so it is somewhat expensive. These are the major diffractions, electron and neutron diffractions, and both are used to study the complete structure of the sample, and this gives a brief information about the types of diffraction. Thank you.